Okay, so next topic is discrete valuation. So this is a so these are some particular type of valuation ring which appear, which are little easier to work with. So remember that not all valuation rings are discrete valuation rings. So there are valuation rings which are not. So these are sometimes you call DVR in short, and they play a very important role, because you will see when you consider algebraic curves, then the local rings are smooth algebraic curve. Local rings are discrete valuation. So local objects are DVRs. Yeah. So recall what is an absolute value on a field. So an absolute value on a field K is a mapping from K to R, say R is a real number, x going to a mod x, which satisfies some property, which satisfies mod x greater than equal to 0, mod of xy is equal to mod of x mod y, and the triangle inequality mod of x plus y is less than equal to mod x plus mod y. So this is actually the Archimedean. So this absolute value. So you call it the absolute value is Archimedean if it has this property, this triangle. So this is a, but it is called non-Archimedean. So instead of this mod x plus, so if you replace, so what I am saying, if you replace three by say 3 prime, which is mod of x plus y is less than equal to maximum of mod x and mod y, then this is all non-Archimedean value, non-Archimedean absolute value. The field is called, if you have a field with such mapping, such modulus function, then the field is called non-Archimedean. Okay, and so a discrete valuation ring actually gives you a non-Archimedean ring. It gives a non-Archimedean field. So what I am saying, that this a discrete valuation DVR on a field on K. So this is definition on K is a surjective map V from K to Z union infinity, say, such that satisfies this property that V of x equal to infinity if and only x equal to 0. So B is V of xy, V of x plus V of y, and C is V of x plus y is greater than equal to minimum of Vx of V. So what I was saying, that a DVR induces are non-Archimedean absolute value on the field K, on K, right. So far I have not told you what is the ring. So, DVR I meant that, oh sorry, I should say it's not DVR, it's a discrete valuation. So, this is called discrete valuation. So, giving a discrete valuation, not DVR, a discrete valuation. So, it's a function, it's a discrete function, so it's a valuation, so this it's called discrete value. Now, a discrete valuation will give you a ring, so that I will call DVR. Okay. So, first examples of discrete valuation. You take K to be the first example which I told before. So, take K to be Q and R to be the localization. Then you define V of P power R M by N to be R. Similarly, for the other one, which when K equal to the quotient K equal to Kx, then define an R to be F by G degree F less than equal to degree G. Then V of F by G, you define it to be degree of G minus degree of F. And I just complete. So, here, so how a discrete valuation induces a non-Archimedean field. So, if I take mod x to be the absolute value to be this mod x to be C power V of x. So, for some C 0 to 1. So, if I give you a constant C which is lies between 0 1 and consider the absolute value of mod x equals C power V x, then you see that if you have a valuation, a discrete valuation, it gives you a non-Archimedean absolute value. So, this is okay. And okay. So, now what I am saying that a discrete valuation gives you a discrete valuation ring. So, okay. So, the proposition, if V is a valuation, a discrete valuation, then V, you take A belongs to K such that V of A is greater than or equal to 0. Of course, this is a sub of this, is a valuation ring. So, as we saw that valuation rings are maximal ideal. So, what is the maximal ideal? Maximal ideal is nothing but all those elements in V which are valuation is greater than or equal to 1. So, this is a proof, a quick proof. So, first of all, V is clearly a subring. This is obvious. And 1, it is a subring which contains 1 because V of 1 is 0. right? V of 1, which is nothing but V of 1 times 1, so which is V of 1 plus V of 1. So this will imply that V of 1 is 0, right? Because of the multiplicative structure. So now what you have to show that if you take a element A in K, either A belongs to V or A inverse belongs to V, right? So suppose A belongs to, so now how about A does okay. So suppose suppose you take a element A in K, so the A does not belongs to V. So what I want to show that A inverse belongs to V, right? So how to show that? So A does not belongs to V imply by definition V of A is less than 0, right? Because V is nothing but all those elements in K are V of A greater than or equal to 0. So now V of 1, which is 0, this is now you consider A and A inverse. So V of A inverse as element of K. So this is V of A times V of A inverse, right? So this implies that V of A inverse equal to minus of V of A. But V of A was negative, so that will say that V of A inverse is positive. So this will imply that A inverse belongs to V, right? And if A is not unit, so another so if A belongs to V is not unit in V, then this will imply that A inverse belongs to V. Sorry, is an unit. Then both A and A inverse belongs to V because of the property that V of A and V of A inverse both are 0. So now, so that means that maximal ideal in V, so if you take all those element A in V such that V of A greater than 0 is a maximal ideal. So it is unit if and only if this V of A is 0, right? So if you take something non-unit, which and this is an ideal, those element, so is a maximal ideal. So this is a rough proof, and so among the so there are some special element you can show that these are generated by a single element, especially if you take element T in V such that if V of T is 1, then this T is called a uniformizer, and any two uniformizer are differ by some unit. So this maximal ideal, actually these maximal ideals are generated by this uniformizer. So this T is called, then in this case T is called uniformizer. And these are called and these valuation rings which appears from these are called DVR, discrete valuation ring. So valuation ring which appears from the discrete valuation, they are called DVRs. And yeah, so and also there are some more properties of this so in other words, this maximal ideal is a principal ideal generated by some uniformizer, and also so maximal ideal in, so these are very similar to PID kind of. There is a what I say in in a DVR, V, any ideals are of the form M power R. M power R is the power of the ideal, where M is the maximal ideal. So, these are some facts that this maximal ideal, this says that maximal ideals are principal. Maximal ideal, not ideals, ideal is a principal ideal. And the generator of this principal ideal is called the uniformizer. Okay, I will stop here with this. Okay, thank you.